So again, for the dual description of an AG code, we need, even for in the rational function field, we need to understand a Weil differential that should satisfy this property. So it has poles at pi's of order exactly 1, and its local components at pi of 1 is 1. And indeed, in Lemma 2.3.6, we will see the existence, even we will be able to describe in terms of polynomials. We can describe such a Weil differential in terms of polynomials. So in the rational function field, to denote the pairwise distinct places, let me consider the pairwise distinct elements from the constant field. And pi denotes the zero divisors of these linear polynomials. And in order to describe such a, in order to set such a Weil differential, we consider the product of all such linear factors, and we denote it by h of x. So here let me note that indeed the principal divisor of h of x can be written as d minus n times p infinity. So in our setting, if we work with d, so this will be related with this polynomial h of x. And we also consider a function, a rational function, whose evaluation at pi's is equal to 1 for each I. And then indeed we can consider such a function, again by the approximation theorem. Such a function exists by the weak approximation theorem. By weak approximation theorem, because we know the existence of a function such that Vpi of y minus 1 is strictly positive, and this implies y minus of 1 minus 1 is in pi, and y of pi is equal to 1. And then by using this function and this polynomial, if we set a Weil differential, which is particularly described in terms of this multiplication of function by the Weil differential, we start here, we start denotes the canonical divisor 2p infinity in the rational function field, and which is particularly considered detailedly in proposition 1.7.4. So we start like in this description. And if we set this Weil differential, indeed we can see that this satisfies these desired two properties. So that means it has poles at pi's of order 1, and its local components at pi's of 1 is equal to 1 for each I. And in particular, its canonical divisor is the canonical divisor of the right hand side, so which has this explicit form. And here by h prime we mean the derivative of polynomial h of x. So that means it's enough to consider the properties, this omega star, which is describing this proposition, and just enough to verify, do we have such a two properties for such a Weil differential. And in order to say that, first, let me verify this Weil differential has poles at pi's of order 1, because if you look at evaluations at pi's of this divisor, means that to look at the evaluations of the right hand side, and obviously since this p infinity is different from this pi's, this valuation is going to be 0. And by the technique of h of x, this is the product of these linear factors, distinct linear factors, its valuation is pi is going to be 1. We have -1 here. And for the derivative for this valuation, let me write the derivative of h of x by first representing h of x as the product of this linear particular linear factor x minus alpha I for fixed I times g of z, here g of x, and here g of x does contain all other linear factors which are different from this given I. And in this case, its derivative by the product group is going to be g of x plus x minus alpha I, derivative of g of x, and derivative of g of x also does not contain any, does not contain the factor x minus alpha I, because since g of x does not contain x minus alpha is a factor. And if we check its valuation by strict triangle inequality, it's going to be minimum of the valuation of gi, this is 0, and this is going to valuation of this product, this is 1, so this is 0. So we can also conclude that this valuation is 0. And finally, we can also see that this valuation is also 0 thanks to the choice of the function y by the weak approximation theorem, because it tells us the evaluation of function y at pi's is equal to 1. So that means y does not have, I mean, pi is not zeros or poles of this function y, right? So that means it behaves like a constant. The valuation of this function at pi is going to be 0. And that means this shows us this Weil differential has poles at pi's of order 1. And now it remains to verify that its local component, its pi of 1, is equal to 1. And again, what we write is that, let me recall that this omega is defined as in this form. And here h of x can be written as this product and its derivative g of x plus x minus alpha I the derivative of g of x. And if we understand this local component, vpi of 1, so that means thanks to this equality, we want to understand the local component of this real differential at pi of 1. And first, by the definition of a local component, indeed what we understand is e to the pi y times h derivative of h of x. So this is why let me analyze and rewrite this statement to understand, to be able to use the dictionary, the proposition 174, I think. So here let me note that this function can be written as just by adding and subtracting 1, and just by writing h of x and h of h derivative of h of x and h of x explicitly. And by opening the parentheses, we will write it 1 minus x, 1 over x minus alpha I y minus y times x minus alpha I So in this case, let me denote it by u, and we can observe that u is indeed a rational function which has no poles at pi's, because we can see that by the choice of, by the choice of the function y, and since the valuation of x minus alpha inverse is -1, vpi y minus 1 x over alpha I is bigger than or equal to 0. So the valuation of this part is bigger than or equal to 0. And similarly, if we check the valuation of this function, because the derivative of g of x and g of x does not contain any linear factor of linear factor x minus alpha, their valuations are going to be 0. And again, thanks to this choice, we know that ypi is a non-zero constant, so that means pi cannot be neither pole nor 0 of the function y. So that means vpi of y is 0, and this shows us vpi of this product is 0. And thanks to triangle inequality, we can see that thanks to this rewriting, this function has this property. That means that it has no poles at pi's. And thanks to the dictionary in proposition 174, in particular, partially for this specific Weil differential V star, so whose divisor is particularly equal to the -2 p infinity. We know that its local components of the functions, particularly in this form, has such valuations. This is u, sorry. This is from proposition 173a, just only checking the valuations. And so that means if we take the local component of a Weil differential of the both sides in this equality, then we obtain VPI of 1 y h prime of x over h of x, or equivalently, if we rewrite what we want to compute by using the definitions of the local components of a Weil differential and the product of a Weil differential by a function, indeed we can see that, and thanks to this expression, this equality, so that means this statement can be written as the local component of a Weil differential at Pi, which particularly contains this function. And in this case, we can see that this is equal to 1. Or maybe I think it might be better to write by using the linearity this is going to be u, and this is going to be 1, and indeed this is why this is equal to 1. And finally, in the last video, we will be ready to describe BCH and local codes more explicitly, particularly if we recall their definitions in terms of a subspace subfield codes of a dual of an AG code. So that means our main purpose is to describe how we can write this dual in terms of this AG code, and how does H look like, can be described by also using Lemma 2, 3, 6.